And I also would, some of you may notice that this actual seminar has got a future date for a lot of you guys, because it is actually February the 7th here in Australia, even though in Canada it's February the 6th. And finally, I just want to acknowledge, I noticed Guy Latouche had logged in. A lot of what I say is not going to be a surprise to Guy, because a lot of it was actually done by him back in the old days, and certainly more recently he and I have collaborated and talked about these things a lot. So a special shout out to Guy. It's really an absolute pleasure to see him here. All right, so let's move on. I've just got to make sure things are going to work. Okay, that does seem to work. Can everyone see the slide change? Let me know. I'll just proceed, and if there's any problem, let me know. So what I'm going to talk about is matrix-analytic models, and these date back to the 1970s and 1980s and Marcel Neuts. Before that, specific models of this type had been looked at, but it was Marcel who sort of recognized that there was a class of processes that you could treat in similar ways. So Marcel proposed a class of techniques for analyzing Markov chains that have block-structured transition matrices. And this class of techniques have become known as matrix-analytic methods. More recently, there's been interest in what are called more general Markov additive models, and in particular, Guy and I have been thinking about these things, along with people like Evgeny Ivanov's. And you can think of these as Markov modulated Levy processes. And with all the analysis of all these, what I find interesting about it is that you require an interaction of mathematical analysis and physical insight, and it plays an important role in the development of results in this area. So sometimes you can't prove things with just physical insight, but you get a pretty good idea of what is true, and then that sort of guides your analysis. And the idea of working this area is swapping from trying to understand things physically to trying to do the analysis, something I find particularly attractive about it. There's a big emphasis on computability of performance measures. That's something that Marcel was always going on about. And sometimes he would argue, that if you write a paper and apply probability and you can't compute the measures you got at the end, then really, why have you done it? So he had a big influence on the discipline that way. Okay, so let's start talking about some mathematics. So I'm going to talk about discrete time Markov chains, but everything that I say can be adapted to continuous time. And in my general experience, discrete time Markov chains are often easier to understand from an analytical point of view, but it's certainly true that continuous time Markov chains are more convenient from a modeling point of view. So it is important to be able to understand both structures. So I'm going to define it, well, Marcel defined a discrete time Markov chain of GIM1 type. It's got a two-dimensional state space. And the first dimension is countably infinite. So it's something like, say, the number of customers in a queue. And the second dimension is finite. So the chain, we can be in a two-dimensional state, Ki. We say that it's in level K and phase I. So the level is the countably infinite dimension and the phase is the finite dimension. And if we order the states properly for a GIM1 type Markov chain, we can write the transition matrix in a block structure as I've shown here. And what that essentially means is that the level can go up by 1 or down by anything until it gets to 0. So this is certainly the count of the infinite dimension is usually thought to be the non-negative integers. So the first row of this is the transition structure at level 0. The second row is the transition structure at level 1, etc. So as you see, you can go up by 1 level, you can go down by any number of levels. And a related structure, a discrete time Markov chain of MG1 type, that's got a state space that's, again, has a two-dimensional state space with a countably infinite level and a finite phase. but it's not block skip free to the right, it's block skip free to the left. So it's got a transition matrix that can be written in the form here, as shown here, where you see that the level can go down by 1, but can go up by any amount. There might be slightly different transition matrices at level 0, but apart from that, it's got the block turplets form. Now, the actual notation here, these days we would label these matrices by the change in level. So instead of all those A naughts, we would have an A-1, and on the diagonal we would have A naughts, etc. This was an adaptation of a talk that I gave a while ago when this other notation was common. And I thought of changing it, and then I thought, if I try and change it, I'm going to stuff something up. So I'm asking you to bear with the notation, but if you were actually doing it using more modern notation, we would index these matrices by the change of level. So what's the point? Well, we use these type of Markov chains to model things. And I'm not going, this isn't a talk about modeling, but I'm just going to briefly mention it so you've got something to sort of hang the structure on. But really the point to note is that from a modeling point of view, the second dimension has got as many uses as you've got an imagination. It can be used to denote the state of independently moving environment. It can be a number of transmitting sources in the telecommunications model. It can be a progress of one or more phase type random variables, so we can model non-Markovian distributions for, say, a service time. It can model the number of individuals in an interactive species model, underlying state of hidden Markov chain. It really is only bound by your imagination. But if you actually want a sort of canonical model to think about, I'd suggest you think about an MM1Q with arrival rate lambda and service rate mu, but imagine that there's an independently moving environment that changes from amongst a bunch of finite number of phases. And so when the underlying chain is in phase I, the birth rate could be lambda I and the death rate could be mu I. So imagine a whole bunch of related MM1Qs where the arrival and service rates change according to an independently moving environment. That's a sort of fairly simple model that you can use to think about these things. So GR1 type Markov chains are skip-free upwards. They can only go up by most 1, and MG1 type Markov chains can go down at most 1. And the intersection of both of them is something called a quasi-birth and death process. So they're skip-free in both directions, and we can write transition matrix of a quasi-birth and death process, or QBD for short, in the form as I've shown there. And it's particularly in this context where it would be better to have A1, A0, and A-1, but I'm going with the notation I had originally. So before I move on, well, I'll just actually, here's a diagram. Now, Guy and I are always arguing about whether this diagram should be pointing to the right or pointing upwards. And we often joke that since I live in Australia and we're the land down under, we always think of going up. So I've got the levels, the countably infinite part of the state going up, and the phase part of the state across the x-axis at the bottom. And the important thing to note is that you can have arbitrarily complicated transitions between phases whenever you go down a level, whether you stay at the same level or whether you go up a level. But this pattern, these transition rates, have to be independent of I. So in that sense, apart from right near the boundary, there's spatial homogeneity here. But before I move on, does anyone want to ask any questions about the model? Okay. So the first question we want to ask about any Markov chain is it positive recurrent? Does it have a stationary distribution, or is it recurrent? And these questions can be answered essentially by what your intuition might tell you would be a first guess. You sort of think, well, it's actually got a structure on the countably, the level variable is countably infinite. So what we really need to do is to talk about recurrence and positive recurrence is to make sure that it doesn't go off to infinity. Or if it does go off to infinity, that it comes back in finite expected time. So what you might guess is that, well, let's talk about the drift upwards and the drift downwards. You would expect that if the drift upwards was bigger than the drift downwards, then maybe it's going to be a transient Markov chain. If the drift upwards was less than the drift downwards, it would be a positive recurrent. And if the drift upwards was equal to the drift downwards, it would be no recurrent. And that in fact is true, but we have to define what we mean by average drift. And the way you do that is you think of the Markov chain that just moves between phases. So that's got a transition matrix A, which is just the sum of all these AKs. So that's really a transition matrix that gives the rates of changing phase if we ignore the level change. And so that is a discrete time Markov chain, and it doesn't actually have to be irreducible, but it does have to be made up of irreducible classes. And we're going to make the assumption that it is irreducible. So let's let X be the solution to XA equals X, which you can think of as stationary distribution of phase, if you ignore the level. Then the chain is positive recurrent, no recurrent, or transient, according to whether this expression is less than, equal to, or greater than 0. And this is actually the net drift upwards. X, A, nor E is the rate of going upwards. This is the rate of going downwards, actually weighted by the size of the jumps. And so you can think of this as the positive drift, and this is the negative drift. And if you look at the difference between them, positive recurrent if the drift is less than 0, no recurrent if the drift is equal to 0, and transient if the drift is greater than 0. So that's sort of a natural condition. I mean, there's some maths to do to prove that, but it's what you might expect is true, and it turns out that it is true. So the famous result that Marcel showed was that if you got a chain of GI1 type and it is positive recurrent, and exists a matrix R such that if we partition the stationary distribution according to levels, so pi naught is a vector that's of dimension m if we've got m phases, and pi 1 is also a vector dimension m. So we've got an infinitely, countably infinitely many states, but we partition it into little vectors of size m that are given by each of the levels. Then pi n is the vector pi naught multiplied by r to the power n. So that's known, that's what's referred to as the matrix geometric form of the stationary distribution for a GI1 type Markov chain. You still need to work out what pi naught is. You can actually write an expression down for pi naught. It's given here. I will explain a little bit later on what this means, but it's essentially this matrix is essentially the matrix, the transition matrix, if you look at the Markov chain only when it's in level 0. And so this is really looking at thinking of the actual stationary distribution at level 0 as the stationary distribution of that partially observed Markov chain. So a lot of people, this is used a lot in engineering and in mathematical biology and lots of other areas. If you can show that a Markov chain of GI1 type, then you know, and you can show that it's positive recurrent using the drift condition, which I've just talked about, then you can actually write down its stationary distribution in terms of this matrix R. Now, of course, we've got to know what R is. It turns out the matrix we're looking for is the minimal non-negative solution to a matrix equation, which is shown here. And this is our first physical interpretation. Turns out that R is a matrix of expected numbers of visits. In particular, the ijth entry of the matrix R is the expected number of visits to phase J of level 1 before first return to level 0, condition on the process starting in phase I of level 0. So imagine you're at level 0 in phase I, you start off your Markov chain. Now, it might go from phase I of level 0 to some other phase K at level 0. If it does, it never visits level 1, so we don't count any visit. But it might go up to level 1 in some phase, say L, and then it might go to a different phase at level 1. It might go up to level 2 and 3 and 4, and then come back to level 1 and visit a few more phases at level 1, and then go up again. But at some stage, it's going to come down. And when it does, that's the end of the count. So what we've counted is the expected numbers of visits to all these phases at level 1 before first return to level 0, condition on starting phase I of level 0. So it's a fairly complicated matrix of expected number of visits before a random time, this return time to level 0. In general, R is a spectral radius which is less than or equal to 1, and the chain is positive recurrent if and only if the spectral radius of R is less than 1. So the genius of Marcel's original work on this that showed that for any GR1 type Markov chain, we've got this matrix geometric stationary distribution, is by actually dreaming up a matrix, this one, that actually satisfies the equation that we would want to be satisfied. So he's come up with a physical meaning, a physical matrix that therefore shows there exists a solution, the one we're looking for, the minimal non-negative solution to this equation. So what about chains of MG1 type? They don't have a matrix geometric stationary distribution. The way we analyze chains of MG1 type is we look at truncations. So let's say we go up, we're interested in the stationary distribution of a positive recurrent MG1 type Markov chain up to some level n. Well, that truncated part of the stationary distribution is proportional to the stationary distribution of a finite Markov chain that's got a transition matrix like this, where we actually perform a truncation to turn the infinite state transition matrix to a finite one, and then we augment the last column with some different expressions, and involved in this is a matrix G. So the way we analyze an MG1 type Markov chain is by looking at successive truncation. And we find this matrix G, and I'll talk about it, construct this chain and find the stationary distribution of this chain, and that will be the exact stationary distribution of our infinite state chain, truncated to the first n level. So this matrix G has also got a physical interpretation. In fact, it's a little bit nicer than the physical interpretation of the matrix R, because G is a matrix of probabilities. And it turns out that the ijth entry of the matrix G is the probability that the chain hits level K minus 1 in finite time, and does so in phase J, given that it starts in phase I of level K. So G is about the transition of the phases at hitting times at successively lower levels. Again, you start out in phase I of level K, you might go up to that, level K plus 1, K plus 2. You might stay the same. At some stage, you'll go down to level K minus 1. And when you do, you're going to hit level K minus 1 in some phase. And so the ijth entry of the matrix G is the probability that when you first get to level K minus 1, you hit it in phase J. So G G has to be substochastic, because if you sum over all the different possible phases at level k minus 1, then that gives you the overall probability that you're ever going to hit level k minus 1. And if G is positive recurrent, if the Markov chain, the infinite level Markov chain is positive recurrent, then you're going to hit level k minus 1 with probability 1. So G has to be a stochastic matrix. In general, it's possible for in the transient case, that the actual probability of ever hit level k minus 1 is strictly less than 1. And that in that case, G is a strictly substochastic matrix. So G is, in general, a substochastic matrix, and it's stochastic if and only if the chain is recurrent. And you can use elementary arguments to show that this matrix G is also a minimal non-negative solution of a matrix equation. This one here, sum from k equals 0 to infinity ak g to the k is equal to G. So I'm just going to get back to the previous equation we had for the matrix R, which is here. And you see, this is really saying that R is a left solution of a matrix equation involving these transition matrices AK. And here, G is a right solution to the same matrix equation. And of course, matrix multiplication is not commutative, so these solutions aren't the same. Now, what about, well, the first comment I would make is that G, as I mentioned, is the matrix of probabilities rather than the matrix of expected values, which R is. So in some sense, it's a nicer object to work with. It's easier to understand. And of course, there is a G and an R in the case where we've got a chain that's both of GIM1 type and MG1 type. So if we've got a QBD, the matrix R can be written in terms of the matrix G via a relationship here. So if you know what G is for a quasi-birth and death process, then you can calculate R. You can write R in terms of G. And in fact, if you've got a general chain of GIM1 type, you can write the matrix R in terms of a matrix G for what's known as the dual chain of MG1 type, which is what you get when you turn the levels upside down. And you go up when you want to go down, etc. So what that tells us is that algorithmically, we can concentrate on algorithms for calculating G. You can actually directly come up with all these algorithms for R, but it's actually easier to think about G, and so that's what I'm going to talk about. And furthermore, to keep the notation simple, I'm just going to discuss the QBD special case. So everything I say is true for the more general GIM1 type and MG1 type Markov chains. It's also true for continuous time Markov chains with suitable modifications. But to get all the ideas over, I'm actually going to talk about discrete time quasi-birth and death processes. So in that case, this matrix equation turns out to be a matrix quadratic equation, and it's given here. We're looking for the minimal non-negative solution to this. Doesn't look very hard. We learn how to solve quadratic equations in school when they're scalars. These are matrix equations, and you wouldn't think it'd be that hard. I mean, you know, a lot of people, when they see this, think about diagonalizing G and using spectral methods and stuff like this, which you can do, although there are some difficulties. It turns out that the equation's got an analytical solution only in a few special cases. It's almost impossible in a general case, even when you think you've got a simple quasi-birth and death process to write expression for G down analytically. So in general, you have to resort to numerical solution. I'm sorry, I've got a few trucks driving by outside, so I hope it's not noisy. The one thing that I actually try and encourage my students to do as mathematicians is to have a go at things, to try and see if things work. I think we're often very conservative at making a statement in maths because we're taught don't say anything unless you're sure it's true. Don't, be cautious. But I think there are sometimes when it's really good, especially from the point of view of getting insight into problems, to just try things. And maybe they work. And if they do work, maybe that gives insight to the sort of things we should be trying to prove. And I think this is the case. So, in fact, I was practicing this talk to my group a couple of weeks ago, and I said to them, let's say you're faced with this equation. You're given a laptop with a lot of, with MATLAB, and you imagine that some bad person's got a hold of your loved ones and they're going to do something nasty to them by the end of the day if you don't tell them what the solution of this is for some specific matrices A0, A1, and A2. So you don't have to think like a mathematician. You don't have to prove that there's a solution. You don't have to do anything. You just have to rescue your loved ones by saying what the matrix G is for some specific matrices. What would you do? And trying something, what would you do? And what I actually want them to do and think about is, what about some type of iterative technique? Maybe this is an equation, so maybe I can just try recursion. Start off with a particular value of G, say G equals 0, and then just iterate. And maybe it'll converge. And if it does, I'll solve my equation. So trying to get people to think about just trying things. And then if it does converge, you maybe ask the question, well, can I show you it always converges? And why would it converge? Now, you're not going to worry about those things if you're trying to save your loved ones. But as a mathematician, of course, you come back and worry about those things. And that's the sort of thinking I think you need to have in this area. You need to be prepared to try things, see what happens, and then maybe subsequently ask why it works. So that's sort of the first thing that Marcel Neuts did. It is true that for an irreducible QBD, you can show that I minus A1 is invertible. And that's because A1 is the matrix of transition rates from a level back to itself. So if you can get from any phase at a level to either a higher level or a lower level, eventually, it doesn't have to happen straight away, then it means you can escape, which makes A1 a strictly substochastic matrix. And therefore, I minus A1, it's got to be invertible. Follows from the Perrin-Frobenius theorem that the maximal eigenvalue of A1's got to be strictly less than 1. So an obvious first approach to solving that equation may be to transform it into the sort of fixed point equation. Maybe I should have said second approach, because I mentioned maybe the first approach is just to try a recursion on this equation itself. But the next approach is to note this, take the A1G over to the left-hand side, and then multiply by I minus A1 inverse, and you've got another expression for G in terms of itself. And here's an iterative procedure that you could use. You could start off with G0 equals 0, put it in here, get G1, put G1 in here, get G2, and just follow that recursion. And in fact, that's what Marcel Neuts did back in the early 80s. And he showed that if you do that, Gn converges to G. And there's always an exception about null recurrent QBDs. And if you want to know about things about null recurrent QBDs, you should listen to the paper that Guy and I actually plan to submit to the MAM 12 conference, which Amir mentioned is going to be in Toronto in the middle of the year, because we plan to talk about these algorithms in the null recurrent case there. What it actually means, except when the QBD is null recurrent, the convergence is linear, which essentially means that Gn, the difference between Gn and G is like gamma to the power n, for some gamma in 0, 1. That's called linear convergence. So technically, if you want to take the limit over the left side, you're not sure that limits exist, so you have to take lim sup. Then you can show this is true. So the type of question I want to spend the rest of the talk talking about is, can we give a physical interpretation to the nth iterate of procedures such as the one described above? Now, Neuts' original iteration, that question sat around for a long time. People didn't quite know what the physical interpretation of the nth iterate was. It actually ended up being solved by Nigel Bean and myself and our PhD student Nectarius Contalian, maybe 15 to 20 years ago, when we were looking at tree-structured quasi-birth and death processes. So it's not a particularly simple iteration, and I'm not going to talk about that one here, but there is a physical interpretation. It's a bit of a complicated one. There are much simpler ones, which I'll talk about in a minute. But before going there, I need to just mention something about censoring. So let's say we've got an irreducible finite state discrete time Markov chain, and we partition the state space into two sets, E1 and E2. This induces a partition of the transition matrix. And actually what we're solving is the equation pi t equals pi. It's irreducible finite state, so it must be positive recurrent. So we know there's a solution to this, which sums to 1. But it turns out that the partition bits satisfy these equations. And the simplest way to see this is just do block Gauss-Jordan reduction on this matrix. You can all go away and do that. And you'll find out that the vector pi1 satisfies this. And then you can write pi2 in terms of pi1 using this. So it's really like writing this in triangular form, like you do when you do Gauss-Jordan reduction. And the only difference here is we're doing it in a block sense. And I minus T22 is non-singular for the same reason that I mentioned I minus A1 was singular, non-singular before. You've got to be able to escape from E2 for this to be irreducible and positive recurrent, which means that T22's got to have a spectral radius strictly less than 1. So I minus T22 first necessary. And when it exists, it's convenient to remember that it actually can be written in this form. It's sum from k equals 0 to infinity T2 to k. So this is really modeling a situation, the summand here, where there are k transitions that go from the set E2 to itself. And this series must converge. So when we write pi1, T11 plus T12, I minus T2 inverse T21, we can substitute infinite series here. And we can think of pi1 as a stationary distribution of the discrete time Markov chain observed only when it's E1. So if you're sitting in E1, you can go to another state in E1 according to a direct transition, E11, or you can have a transition to E2, hang around in E2 for any number of k of transitions, then return to E1 via the transition matrix T21. Now imagine you couldn't see what was going on when you're in E2. So you're just sitting in E1 and you can only see the states in E1. So you don't know what's happening when this happened, and you just think of this transition as happening instantaneously. That's the Markov chain, the discrete time Markov chain observed only when it is in E1. Now, I said the whole thing was finite, but you can actually make similar comments in the case where E2 is infinite, as long as this series converges element-wise. And that is the case when the Markov chain leaves E2 and goes back to E1 in finite expected time. In particular, it's true when the whole Markov chain is positive recurrent. So then the comments I made do hold when the set E2 in the partition is an infinite set. And in fact, it's not just the case that pi1 is a stationary distribution of this discrete time Markov chain, but this here is the transition matrix of this discrete time Markov chain observed only when it's in E1. And that's true even if the matrix is substochastic, when there's a positive probability that it may leave E1 and not return. But you can still say, okay, I'm sitting in E1, I see the Markov chain every time it's in a state in E1. It's possible at some stage it moves to E2 and never comes back, and you never see it again. And the second part of where we write the probability, the pi2 in terms of pi1, we use this. And that's the probability Markov chain first enters E1 in state J, given that it started in state I of E2. So with that information about censoring, let's go back and think about linear algorithms for solving the matrix quadratic equation for G. The one thing we can do is write that basic quadratic equation in a different way. So we split the A naught G squared up. We take one bit of it as a minus A naught G. So the only thing that's not post multiplied by G is the A2. We take everything else over to one side. And for the same reason as I mentioned before, we can put forward an argument that says this matrix is non-singular. So we can multiply by its inverse and write G as I minus A1 minus A naught G inverse A2 and base an iteration on that. Let's think about that, this iteration. So we're starting with G naught equals naught. So the first iteration of this, G1 is I minus A1 inverse A2. So that's what I've got here. I minus A1 inverse is the sum from K equals naught to infinity A1, A2. So what this says is I can have any number of transitions from a level to itself. The ijth entry of this is the probability the chain hits level K minus 1 in finite time and does so in phase J, but it never goes to K plus 1 because there's no A naught here for going up a level. So what we've actually got for the first iterative of this algorithm is just a two-root probability. It has the thing that every entry of G is. It's the probability the chain hits level K minus 1 in finite time and does so in phase J, given that it starts at phase I of level K, but it's got this extra ingredient that level K plus 1 is taboo. This sample path never goes to level K plus 1. And in fact, we can use induction to show that the ijth entry of Gn is the probability, again, that it hits level K minus 1 in finite time and does so in phase J, given that it starts in phase I of level K, but it never reaches level K plus N. So as we go through iterations of this algorithm, what we're actually doing is successively relaxing the taboo level. The successive iterates have the same physical interpretation as that as the entries of the matrix G, but with a linearly increasing taboo level. So that gives us some insight as to why the algorithm converges linearly, because we're linearly relaxing the taboo level. So I've just talked about a linear algorithm that's basically got a physical interpretation about a successively higher taboo level, but a taboo level that moves up linearly. So people didn't stop thinking about algorithms, and in 1993, Guy Latouche, as I mentioned on this call, and Ramaswamy proposed something that they called the logarithmic reduction algorithm, which is much more complicated than the algorithm we've just talked about. Essentially, you could write an expression for G as a sum of products of some matrices that you call U superscript I and D superscript L. And these U's and D's satisfy a recursion. So UL plus 1 is, again, it's one of these things where it's something inverse multiplied by another matrix, something inverse again multiplied. And you notice the thing that we're inverting here, I minus UL DL minus DL UL inverse appears in both of these things. And the UL plus 1's got a UL squared here, and DL plus 1's got a DL squared here. And these start off at U naught in terms of the parameters of the problem, I minus A1 inverse A naught, and D naught is I minus A1 inverse A2. So a lot more complicated. We've got two lots of things, and then we've got to put them all in this infinite sum of finite products. But we've got some familiar things we recognize. And in particular, we got this I minus something inverse. So that makes us, again, think of censoring. So obviously, we can't evaluate an infinite sum computationally, but so let's say we truncate that sum at some finite level, and let's call that Gn hat. Well, what Latouche and Ramaswamy showed is that except when the quasi-birth and death process is null recurrent, this matrix, the matrix of partial sums, converges to G quadratically. And what that means, there exists a constant, gamma, such that the difference between G hat n and G goes up like gamma to the 2 to the power n. So it doesn't go up linearly, it's not gamma to the n, it's gamma to the 2 to the power n. And it turns out this algorithm also has got a neat physical interpretation in terms of taboo probabilities. The ijth entry of the nth iterate is the thing that's familiar, the probability we first enter level k minus 1 in phase j, given it starts in phase I of level k. And the taboo bit is that it does not visit any level higher than k plus 2 to the n plus 1 minus 2. Now, the minus 2 doesn't really matter. So it's got a taboo level of order k plus 2 to the n plus 1. So we get some insight as to why it's quadratically converging, because the taboo level is jumping up at a rate of 2 to the power n. So the taboo level increases exponentially fast in terms of the number of iterates. And so we should at least physically expect that an algorithm that does that is going to be quadratically convergent, which in fact it is. Just a brief insight into how we know that. Well, let's think about U naught and D naught. They're actually I minus A1 inverse A naught. We can hang around in level K for an arbitrary number of times, and then eventually we go up by 1. Or we hang around in level K for an arbitrary number of times and eventually go down by 1. So they're respectively the transition matrices of the discrete time QBD derived from the original one by observing it just at time points where it changes level. So we don't look at transitions that stay in the same level, but eventually when it moves either up or down, we record that. So it's we can think of this as a discrete time Markov chain that's got a transition matrix about going up of U naught and a transition matrix going down of D naught, and it can't stay in the same level because we only look at this Markov chain when the original one changes level. And you can use induction to see that these matrices U and D are actually transition matrices of the discrete time Markov chain, the original one, that we get if we look at the original one only at the time points in which it hits levels of the form k plus m times 2 to the L plus 1. So again, it's about taboo. We look at the original Markov chain and we look at it just at particular time points, and there when it hits these levels that are actually going up in a sort of coarser grain. The difference between this is 2 to the L plus 1 between each level that we actually observe the chain. So we can see the summand on the right-hand side of this I equals 0, L minus 1, U to the I, D to the L. What it actually does is looks at sample paths. When the I equals 0 term, we've got a U naught, so that looks at the transition when we jump up one level. And then we've got a U1, so that looks at a transition that jumps up 2 levels. And then a U2, which looks up 4 levels. So the next term here is K plus 3, all the way up to K plus 2 to the L minus 1 levels, all without ever going back to level K minus 1. And then it hits level K minus 1 without ever going up the extra level to K plus 2 to the L plus 1 minus 1. So it's about taboo probabilities. And that's the sum. And if we sum that over L's, we take into account all levels going up to this height of 2 to K plus 2 to the L plus 1 minus 1. So that was an insight, a physical insight of Ram and Guy. They published the logarithmic reduction algorithm. Guy's been working a long time with Dario Bini and Beatrice Maney. They work in applied probability, but they're actually experts in numerical analysis. So they were the people who got the numerical analysis community interested in these problems. And there's a thing there called the cyclic reduction algorithm, and they adapted this technique to the calculation of G. And it uses a similar censoring idea to the logarithmic reduction algorithm by essentially looking at powers of 2, levels of, looking at the original chain when it hits levels that are powers of 2 apart. But it actually organizes the calculations in a slightly different way. Essentially a different version of the logarithmic reduction algorithm. And the numerical analysis people have got a bunch of speed up features you can use. You can transform matrices to move eigenvalues away from the unit circle. You can use fast Fourier transforms. And in fact, if I had to do this, I wouldn't try and write my own code. I would go to Benny Van Hout's website. Benny's at the University of Antwerp, because he's got a website that's got state-of-the-art MATLAB code for doing these things. And Mayor, can I just ask, because I've probably got about 10 minutes to go, is that okay to keep going?
I would personally be fine, but I don't know about the audience. Maybe we can continue, and in case, as we are recording, those who have to leave, they can refer back to the recorded video.
Yeah, okay, I will keep going. I can certainly do that, but very sorry because I missed that. I think I would have been on time, but obviously now I won't be, but let's keep going. Okay, the final bit I want to talk about is Newton's method. So we go back to Guy's linearly convergent algorithm. We use the fact that the original matrix quadratic equation could be rewritten this way. And we could apply Newton's method to the solution of this equation. And Newton's method, if it works, is supposed to be quadratically convergent. So maybe there's another quadratic convergent algorithm we could use to solve this. When you do that, and I'm not going to explain how, applying Newton's method to solving that gives you an iteration that's much more complicated than the ones I've talked about before. If you look at this, I've got some mess of matrices, but they're all got a superscript n. So you can think of it when we're actually trying to evaluate n plus first iterate, gn n plus 1. I'm using g subscript capital N to be G Newton's method. This has got the variables on the left-hand side. You can think of all of this on the right-hand side as a constant. We can write these UNs in terms of previous GNs. So this is a big, long thing that's got complicated stuff, but it's all at iteration n. We start out with Gn of 0 equal to 0. So that's what happens when you apply Newton's method. And what you need to do is solve a pretty weird linear equation, because you're solving for the variable matrix G, but this matrix G is stuck between coefficient matrices that pre-multiply it and coefficient matrices that co-multiply it. And there's no guarantee that these matrices are non-singular, so you can't multiply by their inverse to get rid of them. So this is known as a Stein equation, this equation dagger. And the difficult part of implementing this algorithm is that each iteration, you've got to solve a Stein equation to get Gn plus 1 in terms of Gn. In 1994, Guy showed that for any initial matrix G0, the sequence Gn converges monotonically and quadratically to G. So that's good. It does do what we expect it's going to do, converge quadratically. So he then decided he was going to implement it. And what he did is transform this equation that's got the G stuck in between these matrices. What you can do is concatenate the columns, write that as a vector, and then you can write the coefficient matrices as a direct sum of stuff and solve for that vector and then reassemble it as a matrix. And he did all that, and he provided an algorithm for evaluating the sequence of matrices. And it turned out that each iteration of that algorithm had a complexity of order m to the 6, where m is the number of phases. So that wasn't a very efficient thing at each iteration. He tested Newton's algorithm against the linearly convergent algorithm, the first one. He found that while Newton's algorithm required up to an order of magnitude fewer iterations, it could take up to an order of magnitude longer in terms of computer time. So, yeah, sure, Newton's method converges quadratically, but it takes so long to do each iteration that it's not practical. And it would be fair to say that conventional wisdom in the Matrix-Analytic community was that the complexity of each iteration makes Newton's method uncompetitive. And later on, when Guy and Ram came up with the quadratic convergent logarithmic reduction algorithm, and then Dario and Beatrice came up with the cyclic reduction algorithm, that just reinforced that. So people didn't pay attention to Newton's method. But in fact, if you really knew your numerical analysis, you could have done that iteration solving that Stein equation, the equation dagger, with an m cubed algorithm, not an m to the 6th algorithm. And it turned out, I've heard this actually, it was in a referee's report of another paper I was writing, where it was a throwaway comment by the referee that there was already this algorithm in the numerical analysis literature that could do this. So that motivated me to go and talk to Guy about it and ask, well, let's revisit how useful Newton's algorithm is. And we wrote a paper where we compared it, and essentially Newton's algorithm is competitive with the others. It does take a long time to do each iteration of the algorithm, but you have to do quadratically fewer of them. But the bit I want to talk about now is, can we give a physical interpretation for Newton's method in a similar vein to the physical interpretations that I discussed above for the linear and logarithmic reduction algorithms, which are in terms of retreating taboo levels? And it turns out you can, but it's not about taboo levels. So like the methods discussed above, the iterates Gn contain probabilities of sets of sample paths that start in level k and end in level k minus 1. But they're not defined in taboo levels like they were for the previous methods. And we need to look at sample paths in a different way. And I'm going to try and explain this, and that's the end of the talk after that. So I think the physical interpretation of Newton's method is really interesting. So let's use some notation. We'll denote the set of sample paths taken into account in the nth iterate of Newton's method by psi n. And remember, these are sample paths that start in phase I of level k and end in phase j of level k minus 1. They're all about probabilities of that event happening, but it's along certain sample paths. And in the other algorithms, we've seen that sample paths gradually get relaxed according to a truncation level. Newton's method, what's happening? Well, U0 is I minus A1 inverse. And G1 is then defined as the solution of an equation like G1 minus this equals U0 A2. And what we can do is successively substitute the right-hand side into the second, so substitute this expression for G1 here, and then successfully do that. And we can say that G1n is actually, we can think of it as the sum from L equals 1 to infinity of U naught A naught, which is I minus A1 inverse A naught to the power L minus 1. So we've got L powers of this, and then, L minus 1 powers of this, and then L powers of I minus A1 inverse A2. And these are matrices observing the Markov chain every time it goes up by 1, and these are Markov chains observing the original discrete time Markov chain every time it goes down by 1. So we're not observing what happens when it stays the same, but what this really says, the summand says, we're looking at sample paths that go up L minus 1 times from level K, and they go down L times till they get to level K minus 1. So sample path that goes up and then down. It's allowed to stay the same on the way, but that's all. So in fact, psi1 accounts for sample paths that start in level 1, increase to some level L, possibly remaining in any level on the way, but never dropping back. So they should say start in level K, not level 1 here. Possibly remaining any level along the way, but never dropping back, and then decrease to level K minus 1, again possibly remaining in any level, but never increasing. So what they really are is what we call single peak sample paths, but there's no limit on how high the peak is. So sample paths in psi1 are all sample paths that look like this. They start in level K, maybe they hang around for a bit, jump to K plus 1, hang around for a bit, jump again to K plus 2, go up some height, and then they have to come down. They're allowed to hang around on the way, but they're not allowed to go back up again. Come down, come down, come down, and eventually you go down to level K minus 1. So that's what the first set of sample paths are, the ones taken into account by GN1. If we make this matrix U1, and it's of the form I minus something inverse, which we can write as, sorry, I've made a mistake there. It shouldn't have the I minus here. It should be S equals 1 to infinity A1 plus A naught G1 to the power S. That accounts for sample paths that have any number of transitions between states, or they're allowed to have a single peak, because an A naught goes up by 1, and then it has a single peak sample path to come back down again. So we can either have transitions from a level back to itself, or we can have transitions that do a single peak along the way. And then if we write G2 in terms of G1, we get that the paths that are in G2 and not in G1 are, if you like, just like single peak sample paths, except what we govern as staying at the same level is not a U naught A1, it's now a U1 A1. And same for going down, it's a U1 A2. And then there's this other term, which I'll mention a bit in a minute. What these sample paths do, the sample paths in psi2, not in psi1, they're a succession of sample paths that either stay at the same level or have a single peak excursion upward. They're each going one level higher, up to some level L. And then you have a succession of sample paths that either stay at the same level or have a single peak excursion upwards, each shifted one level lower until it gets back to K minus 1. And that second term is really there just to ensure that we don't do multiple counting. And the actual argument about why you're not doing multiple counting is pretty complicated, and I'm not going to try and go into it. I just hope that you take my word for it, that that's what the second term does. In fact, sample paths in psi2, not in psi1, are single peak sample paths, but at each level, instead of just staying at the same level, we're allowed to have any number of single peak excursions upwards, but nothing more complicated than a single peak excursion upwards. So if you like, we've got a single peak of single peaks. And then if we look at it for general n, we get a similar expression. They're made up of sample paths which are taking into account how complicated it was at the last iterate. And you have using phi naught to be these sample paths that were taken into account at the previous level, but shifted upwards. You get a whole bunch of sample paths like this, each shifted one level up, and then a whole bunch of sample paths, each shifted one level down. And again, the second term just ensures you're not doing double counting. And so, again, we have a succession of a single peak of sample paths where the sample paths at each level are allowed to be as complicated as they were at the previous iterate. So the way to think about Newton's method is instead of progressively including more sample paths by relaxing at taboo level, Newton's method progressively includes more and more complicated sample paths. And it does that in a sort of fractal way. The basic units of paths at one iteration are the sets of paths that were accounted for at the previous iteration. And when you start thinking about this, you realize that very complicated paths are taken into account within a few iterations. And that, again, it's not proving anything, but it intuitively supports the fact that Newton's method converges quadratically. Not, as I mentioned before, because we got a taboo level that's moving away at a quadratic rate, but because we're really including these very complicated sample paths very quickly. And that's the final slide I've got, so I'll stop there. And thanks for listening, and I am again very sorry for the transmission dropping out in the middle of the talk. I'm happy to answer questions, and I see Guy's asked one, so he'll probably say that I've got something wrong because he knows this stuff intimately. So, Guy, can you ask a question?
Maybe he tried to clap and he pressed a
Maybe he did.
Because
May I ask a question?
Sure.
Hi, Peter. Thanks for the nice
Jimmy,
talk.
how are you going? Yeah,
I'm doing well. My question about this physical interpretation. Let's take the last one as an example. Actually, I think my question is simple. Is this physical interpretation unique?
I think it is for Newton's method because you sort of construct it by looking at, you know, equation. Probably the easiest one is the one for that.
Right. I'm asking this
clear.
question.
Yeah.
I'm asking this question because I noticed that you rewrote the original expression in this summation form, right? Then based on that summation form, you draw this kind of physical interpretation.
So we wrote the G as like this. Yeah.
That's right. If someone else could rewrite this in a different form, would that lead to a different physical interpretation? So that I also believe it's unique, but I was thinking what someone else can do that. Would that lead to a different interpretation or not?
Yeah, look, I guess you're right. I would agree with you on that. It's the one that I thought of, it's the one that Guy thought of. Whether there's another way to rewrite an equation, the iteration for Newton's method. I mean, this first step is not so complicated. And so it's a natural thing to do. And when we looked at it, we wrote it like that. So if someone else thinks of something else to do with that equation, you've got to remember that you can't always say these matrices, these individuals ones, which are U0, A2, and U0, A0, they're not necessarily non-singular. Those matrices, you've always got the G trapped in the middle. So you can't do things like multiply by inverses, which a lot of people are tempted to do when they look at things like this.
May I comment? I think that there should be many different interpretations. The reason I believe that is the time we spent going from the representation that you had written with one summation and then a negative term to remove all the double counting. So we eventually had a formulation in terms of sets of trajectories which only contained new trajectories, and we didn't have to do the removal of the double counting. I believe that it should be possible to do this partitioning in a different manner.
So there we go. I would take Guy's word for that. I'm sure he knows. I see Benny and Amir have got hands up. Are they asking questions?
Yeah, if I may.
Benjamin.
Thank you. Thanks, Peter. Great talk. I was wondering if you are aware of some attempt to use this physical interpretation to develop some simulation in order to assess anything about these models?
In other words, you simulate single peak sample paths or ones with truncation.
Something like that.
Yeah.
Yeah, yeah.
I've never heard of anyone doing it for simulation. I guess you could, yeah.
All right.
You might have to have a reason to do it. I mean, what you can do actually is use these all things like to prove that there are solutions. You can use it analytically. It's the sort of thinking we've used is actually what you use to prove that we're actually looking for the minimal non-negative solutions. So they do have a lot of other uses understanding these things physically. I guess if you want to simulate simple sample paths, like ones that don't go too high or something for some reason, then yeah, sure, you could do that.
Yeah, yeah. All right, thanks.
Thank you very
And
much for the talk. I know the focus was on the G matrix, but I would like to ask a question about the R matrix. You presented the physical interpretation of that. For a while, I was thinking about if the inverse of R exists, what would be the physical interpretation for that? And I tried different things, but all my attempts were to no avail. I was wondering if you have any intuitions into the inverse of the R matrix, of course, if it exists, and to that end, how far can we push the existence of a physical interpretation?
Yeah.
Have you finding?
So inverse of R. R is a matrix. Let's say we're looking at R in a, I'll just go through to a, well, let's look at R for a QBD. Okay. So R is a matrix of expected values of Sogin times at the next level, given you start at level K plus 1, giving you start at level K. So the actual data with the problem that involves transitions that go up are stored in the matrix A naught.
Yes.
So R is invertible if and only if A naught is. And a piece of advice I got from Marcel Neuts a long time ago is that you should never assume an off-diagonal block in a block-structured Markov chain is invertible. Because most models it's not. The diagonal matrices A1 are always invertible because of irreducibility considerations, and you can always get. It's tempting to think that A naught is invertible, and if it is, you can solve your matrix quadratic equation where it is quite easy because you just be multiplied by A naught inverse. And there are people who do those, but I think myself, I mean, if you, for instance, think of an M Erlang 1Q, then you know, some of these matrices often have only got a single positive entry and everything else is zero. So it's not very common. I mean, you can dream up models where they're invertible, but I think, and obviously they're special, but you're probably looking for algorithms that don't make that assumption. And in fact, that's one Guy and I have been talking to people in the Markov additive model community. They are very tempted to make that assumption, but I don't think it's a good assumption to make. I don't know if Guy wants to comment on that.
I think the to have non-singular matrix above the diagonal is not, I mean, it's something that does happen whenever you have some sort of change of the level without a change of phase, which happens in many models. Then you do have A0 being non-singular and you can do things. But I don't think that you need that assumption in order to get understanding for the physical description of the algorithm if you want to compute directly the matrix R. I mean, I think the first time we worked together, it was about an algorithm that you were designing for the matrix R. And it was much more complicated to follow because with the matrix G or U, you are thinking in terms of the probability of something happens at one moment when you do get to the level you are interested in. It's really simple. When you think in terms of the expected time that you spend at one level, then all of a sudden it becomes more complicated to make sure that you don't lose anything or don't add anything that shouldn't be there.
Thank you very much for the insights. Any other questions from the audience?
Maybe one other point I'd make about that. I do a fair bit of work on level-dependent quasi-birth and death processes, which is where these matrices A0, A1, and A2 actually depend on the starting level. And when you do that, you realize that you don't have to have the same number of phases at each level. And that makes all the off-diagonal matrices possibly not square. You still have to have square matrices on the diagonal. So again, for me, the not square ones, then what does it mean to say they're invertible? I mean, okay, you can give interpretation in terms of null spaces and stuff, but they don't, in a general level dependent QBD, you don't need to have the same number of phases at each level.
Yeah, actually, I've had that experience as well. Yeah. And the only time that I had A0 being invertible was the case that Guy mentioned, and that was that level change did not change phase. And actually, it was that problem that made me interested in the possibility of interpreting R inverse to see if I can calculate R inverse based on its physical interpretation.
Yeah,
it's
that's
very,
a good question. Yeah,
and yeah, maybe those examples are limited, but yeah, that's exactly how it came to my mind. And it was a queuing model. Change of level did not change phase, so I had a diagonal square matrix as A0, and it was level dependent. And yeah, so I thought maybe if I could find a physical interpretation for R inverse, then everything else is going to fall in place. But I could not figure that out.
Right. No, that's an interesting question.
Did you? I think that in one of the slides there was an expression of R as a function of G.
Yeah. For QBD.
Yeah.
There.
Yeah. So if A2 in this case is non-singular, what is A2?
A2 going down, right?
Yeah, I think I had A0 going up.
I think you've got your indices mixed up there.
It's not impossible. they're not going
Anyway,
up.
if you start from that equation properly written, you can invert everything if you make the assumption that the matrix A2, that the first matrix is non-singular.
One, yeah.
Have you tried having an interpretation?
I'm not sure if I tried
based on that.
I'm not sure if I tried this to come up with any physical interpretations. No, I don't remember. But that's definitely, yes. It can be a good start point. Thank you. Thank you very much. Are there any other questions or additional points? I personally really enjoyed the talk. Thank you very much. I hope it was beneficial to others as well.
So do I, and again, I'd like to apologize for dropping out. It's so annoying when things like that happen.
I think that's totally fine.
Yeah, I've got to say, I really appreciate the fact that a lot of you guys are up late. It's early morning for me, but it's late for a lot of you, and I really appreciate the fact that you stayed up to listen. So well done.